All right, so it's my pleasure to introduce today Aaron Donahue, who has been the co-lead for the Scream and EAMxx model development since its inception. And he, in his spare time, is a deputy group leader for the climate modeling group at Lawrence Livermore. And a fun fact about Aaron is that even though he's spending his time doing atmospheric modeling now, he actually got his PhD in storm surge modeling uh, from Notre Dame. And before that, he got both a bachelor's and a master's degree in applied math at various places. And so today he's going to tell us how the EAMxx code works. So take it away, Aaron.
Thank you, Peter. Good morning, everybody. Thank you for inviting me to give this talk. It's my pleasure to talk about this infrastructure that we have been designing, developing, testing for the last, I think, like 4 or 5 years. I will say just at the onset, this is actually a pretty big topic. There's a lot that went into the EAMxx infrastructure, so I'll only have a chance to sort of scratch the surface. But my hope is that this talk will introduce everyone in the audience to sort of the design choices we made and help them better understand when they finally get to the point where they're looking at the code or just interfacing with the code and kind of just understanding the philosophy that we took and and I'll give some examples of exactly how we use it so that sort of give us a starting point. Another thing I'll note is that we're all familiar with Scream as the project name, but I will refer to EAMxx this whole time. EAMxx is really what we call the actual fully model infrastructure itself. And of course, that's similar to EAM, which is what we call the atmosphere model infrastructure that we currently have in E3SM v3. So to sort of give us a baseline to understand what I'm talking about when I talk about the EAMxx infrastructure, I'm really talking about what I'm going to call the EAMxx atmosphere driver. It's the driver of the full atmosphere model. For those of you who are familiar with EAM, this would be kind of like CAMComp, right? This is kind of where all of the machinations of the atmosphere model are controlled and sort of scheduling is done. And basically the atmosphere model is essentially controlled. And this cartoon here illustrates kind of the key features of the atmospheric driver. Starting with the left, the driver is responsible for communicating with the coupler and thereby communicating with the rest of the Earth system model. It's also responsible for managing the internal physical processes that we would like to see move through the model. So as the simulation progresses, the atmospheric driver is really involved in making sure that the processes that we want to call are called, that information is being passed properly between those processes, and that we're really getting from it the information that we want. The driver is also responsible for interfacing with us, the user, via runtime options. So the driver provides the options that we can use. It parses the options that we provided and makes sure that the configuration that we believe is being run via the runtime options are in fact being executed inside the model itself. The driver is responsible for communicating with our input-output library. In our case, it's going to be Scorpio. But in general, it just is responsible for kind of managing input and output, making sure that you're interfacing with Scorpio, bringing in the data that the driver actually needs, and providing the data that the output would need based on user specifications or sort of default outputs, such as like restarts, for example. And lastly, especially in EAMxx, the driver plays a critical role in testing, making sure that our code is verified, validated, and giving the user tools to commit that testing. So that's what the driver is sort of holistically, but let's kind of drill down in on what the current driver actually does in kind of this capacity. And this is important because it sort of tells you kind of where we started when we had this project given to us. And we thought of this as, since we were going to have to rewrite everything in C++ Cocos, this was an excellent opportunity to sort of build upon EAM and kind of take the great parts of EAM and make sure that they were being utilized in EAMxx, but then kind of identify some problems or some difficulties with the current driver framework and build upon those and improve those. And so I'm going to start by looking at the current EAM paradigm. And so maybe just in a word, if I could encapsulate my experience at least, and I think the experience of others based on conversations I've had, is that EAM, the current paradigm, is rather opaque. As a new user, as a new developer coming to the code, it can be very difficult to parse. There's sort of a need for expertise in order to really be able to drill in and start making changes to the code itself, to develop within EAM. And that's sort of, I'm going to illustrate that kind of stepping through all the different pieces of EAM and how they can be themselves kind of difficult to work with. And so I'm going to start here with these orange boxes, which represent the model state. And there's essentially 4 different structures in EAM. We have the physics state and the physics tendencies. We have the dynamic state, which is different than the physics state because the dynamics is run on a slightly different grid, and so there's a different configuration. And then there's this thing called PBuff, the physics buffer, which is sort of a catch-all that where we put all the variables that we can't justify putting in the 3 I've just mentioned. But the most important takeaway from this is that as a new developer, you come to the code and you notice that there are many different places that the kind of data or variables that you want to interface with or you want to use could be stored. And there's different ways to add them. So in physics state, physics 10, dynamic state, you have to hard code those variables in. In PBuff, there are functional calls. And then PBuff itself is kind of rife with a lot of opacity in the sense that it's not clear what is in PBuff without going through a series of greps and kind of parsing through a lot of data, which is something that I did early on when I joined the E3SM project. And so I have a firsthand experience with this. Moving on to just how the simulation runs, we have a series of routines. We have the step on series, we have the phys run series. The phys run is at least understandable in the sense of its name. It's physics, and there's sort of a before and after coupling component. That's the run 1 and run 2. Step on is dynamics. It's not clear from the name, but but that's what it's for. And step on is so much more than dynamics. It's also responsible for remapping physics data to the dynamics grid. Is responsible for taking the dynamics data and putting it back on the physics grid, changing some of the geopotential and other geographical or geo variables as well. So step on does a lot, and it's not clear just from the name or even just the understanding that it's dynamics that that's what's actually going on. So again, we see this kind of pain point for entering into the model. If you were responsible for adding something new to the model, it's not exactly clear looking at these routines where you would want to do that and what kind of dependencies you might be accidentally messing with if you were just to make a change in one where you were supposed to make a change in multiple. I've already mentioned that there is this sort of step where we also couple with the component coupler, and so we have to also kind of massage the data into a format that the component coupler can use. The component coupler gives us data. We have to unpack that data in a way that the atmospheric processes can use. And then we have this little wrinkle where inside of a process itself, you might see phys state and phys 10 sort of show up, but they're not phys state and phys 10 in the classical sense, the actual physics state that the entire atmosphere model is seeing, but they're just a recycling of the phys state structure, which is built in order to have a local variable or a local tendency to do something with. And again, as a new user, you might see this and see phys state and not be quite clear understanding that by someone adding the numeral 1, we're not talking about the original phys state anymore. This is just a local variable I'm using for my own purposes. And so again, a little difficult to kind of work your way through as a new user. And then lastly, there's output. And this is not something we interface with often, but if you did ever have to interface with output or just try to understand exactly how the output works or maybe add a new functionality to output, that's also very difficult. There's a number of different files and different routines that all have to do with output. They don't have a standard naming convention for variables, so you have to kind of translate the different names of the variables as you go through the functions. And so it can be really difficult to get at. And so if I were to just kind of summarize everything I'm discussing here, these are kind of the main pieces of the current EAM paradigm that we saw an opportunity to improve upon in EAMxx. So there's hard-coded process order, and so if you want to reorder the processes, was my first project with E3SM. It's incredibly difficult, and you have to do it essentially by hard coding. It's hard-coded time splitting, and as we sort of look to the future of E3SM, I think one of the ideas is how can we change the time splitting to extract better performance or extract better accuracy? And again, here in EAM, we have hard-coded time splitting, so it's a little bit more difficult. It's difficult to add new processes. I've already talked about that. It's difficult to audit just because looking at this diagram, it's difficult to kind of necessarily follow the pathway of simulation or of the data as it passes through the simulation. And I mentioned this as well, that is all the individual pieces are dependent on the rest of the model. So if you want making one change, it's not clear how that would impact other places in the code because there's this dependency. Another aspect of the dependency, which I'll touch upon at the end of the talk when I talk about testing, is that in order to even test a small piece of the puzzle, you actually have to build the whole model. And anybody who's ever built E3SM knows that this can be a time-consuming process. And so it really kind of inhibits rapid development or rapid debugging because you find yourself having to go through the process of rebuilding, resubmitting, waiting through the queue, and then getting your results. And that can be a real big slowdown. So these are the things that we wanted to improve upon in the new EAMxx paradigm. So the rest of the talk is really going to run through these different individual pieces and really kind of emphasize what design decisions we made and how that impacts us, the developer, or us, the user. And so these first two are really for us, the developer. And so going back to that old paradigm, so we have the orange and the green box representing the variable states and the green box representing the functions that are really calling those processes. So tackling the data, we really wanted to figure out a way we could unify this, right? So that when you go and look at data, it's all in one place. It all has a similar structure. And so it's easier to interface with. It's easier to understand. And taking advantage of the C++ aspect of EAMxx, that we could create class objects, we created this field class and these field objects. And so every persistent variable, every variable that you want to sort of be stored for the next time step or to be passed between processes or as output is an instance of a field object, and they're all of the same type. And then we have this field manager class, which is responsible just for managing those. That's exactly what the name implies. And this simplifies operations on variables considerably. It also simplifies just understanding what a variable is. Now, I've told you now what a field object is. I'm going to jump into exactly what is in a field object and kind of, I think it shows exactly all the power of switching to this class object approach rather than having sort of like a structure like we have in Fortran. So what is a field? It is a class object, and it stores not only just the data itself, which is of course what we need in order to run the simulation, but it stores like a significant amount of metadata and has the flexibility to allow us to add more metadata. So we don't know what future applications are going to want to do or what future applications are going to need to extract from, say, a variable. So we've basically made it so a field object, when that application comes around, they can add metadata to it and then use that metadata as they want. So this is an artist depiction here at the bottom here. So this is not exactly what you see when you look at the code, but I think it's helpful to illustrate kind of what's in a field. All this metadata. So it, of course, stores the data pointer, which is directly to, there's the data, there's the information, there's the real precision values in some array. But it stores things like name and units, the layout, the grid that this particular field is residing on. And really importantly, we've included the customers and providers, which really are the processes that want this field, that need this field, and the processes that do something to change that field or provide that field for others. And when I get to later in the talk, that'll make more sense of why that's really a valuable piece of information. Also, this allows us to have universal operations for all fields. So for example, we have property checking as a separate function that works on just any field. And property checking allows us to define something like, I want this field to always be positive. For example, for temperature, you might say, I want this field to always be over 200 degrees Kelvin or 150 degrees Kelvin. Otherwise, something's wrong. And so we have this generic property checking function that can be called on any field. We just define the specifications. And then we can call that and make sure that, say, for example, after one of our processes, that the temperature is always above 150 degrees. If not, throw in air, for example. It also allows us to do things like quickly clone a field. So going back to that example where you wanted a local version of a field because you needed to do something in your process that's kind of a local operation but doesn't really want to change the model state, you can clone it. And that's a little bit more obvious when you look in the code. Oh, this is a clone of original state. Arithmetic operations, for example, adding two fields together, remapping, and then just checking the metadata. So if someone asks for T-mid, but they ask for it in degrees Fahrenheit, which is strange, but let's say they do it, well, we also know that somewhere else T-mid is defined as degrees Kelvin. And so then the model will say, whoa, there's a discrepancy here. And so it kind of hedges against human error as well. So we have the field, and then we kind of take that same experience and we say, how can we apply that to the functions, to the processes, to the actual, the meat and bones of an atmospheric model. And so we have this atmospheric process object. So it's fairly similar in flavor to a field object. We have a class object that represents an atmospheric process, be it physics or dynamics. So macrophysics, microphysics, radiation, all of them from the perspective of the atmospheric driver are just instances of this atmospheric process object. And again, we get that same flexibility. Where we can have generic functions that work on any atmospheric process. So that allows us to do also atmospheric process checking, for example. And really the power is in the driver just sees processes as being an atmospheric process, which it can work with. It doesn't need to know that this is microphysics or macrophysics or radiation or dynamics, and it has to do something special because of that particular process. From the driver's perspective, nope, that's just a process that I call. And so we can do things like reorder our processes on the fly, or basically at runtime. Because again, the driver doesn't need to know exactly what it's working with. It doesn't say like, oh, I'm supposed to be calling my deep convection scheme now, for example, or something like that. It just wants to call the processes in whatever order we ask it. It also allows the driver to define certain aspects of how you call a process. So for example, subcycling is another thing that the driver controls now. So the driver says, oh, I want to call this specific process 4 times per time step. I know how to do that. Sequence order, the grid that the process is being called on, all of these things are managed by the driver for this arbitrary atmospheric process. And so if we dive into what exactly is an atmospheric process, it's the same kind of idea, same artist depiction, right? It is the process itself, but it's really the interface to the process. And it also collects a lot of metadata. And so you have the name, the type, the grid that it's being called on. And that allows us to have checks like, if this is being called on the physics grid, are all the fields that it's asking for also on the physics grid, these kinds of things to really hedge against any kind of developmental error, human error, or just kind of those hard things to debug. And again, I would draw your attention to some of the metadata that I think is really important, such as inputs and outputs. So here we're saying that the process stores, this is the data I need. So this data better exists by the time I get called. And this is the data that I plan to provide to the rest of the model, right? And so that gives us, and I'll show you in a couple of slides, where we can really put that to use and really help developers. But really, it all distills down to those last 3 in that black box there, that you have an interface that has an initialization, a run, and a finalize. And that is what the atmospheric process itself, or the atmospheric driver, intends to call. So you as a developer have your new microphysics scheme, your new macrophysics scheme, all built. And what you need to do in order to interface with EAMxx is just to design the atmospheric process interface, to specify the initialization, so what needs to happen at initialization, what happens during the time step call, and if there's anything to do at finalization, you have that capacity too. And so it really just kind of simplifies that interface layer to the user. And this is meant to facilitate physics interoperability, so to hopefully speed up the time to taking a new process and being able to use it in EAMxx. So going back to my slide a couple slides ago, we have these fields and these atmospheric processes, and on the left-hand side, we have a more simple setup. So if you want to add a field to the field manager, there's one call, add field, and we do ask that you kind of imply your intent. So there's kind of similar to Fortran, an in, an out, and an in-out style to it, and that just really populates that metadata that I was showing you before. And similarly, if you look in the green box, we have these nice simple call sequences. There's only 2. Most developers are not going to do anything with the AD. That's really kind of in place. And so when you're coming to EAMxx and you're trying to add a new process, it's going to be really in those last 3 calls, the AP initialize, the AP run, and the AP finalize. Now, granted, I'm saying AP but here, but you'll give it its own name. But your initialize, your run, and your finalize are the things that a new developer will interface with, and then the driver will just pick up the rest of the slack and make things work. So going back to the current EAM paradigm, and now looking at the new EAM paradigm. So we have this field manager. I didn't talk about the memory buffer. That's really for lack of time. That's a whole different aspect. It's really for local memory. I'm happy to talk with anybody about that when they get to that, when they want to know more about that. But really, we have these sort of like memory, data management. We've got the driver that runs it all. It also interfaces with the coupler and kind of just a simplified interface for even output, for example, which I'll talk about in a couple of slides. So simpler, increased runtime options, interoperability, and then really importantly, independence. Since atmospheric processes are sort of agnostic, they are also able then to be kind of built independently. This is going to be really important for testing. And just to sort of show some of the strength of this approach, I just want to direct to one aspect, one feature that we have implemented in EAMxx. So what we're looking at here looks maybe a little overwhelming in the figure, but I don't really want you to focus on the figure in the focus, but just kind of in general. This is a directed acyclic graph that is generated by default by the code, and essentially just stores an information, all of the processes that are running, the flow of information from one process to the next, so sort of the ordering, and the fields that are being used within those processes and how those fields are being used. This is an incredibly useful tool just for understanding what's happening in the model, but especially for debugging. So for example, if you were looking at your model results and you're like, something is really off with temperature. Now, if you were in the old EAM paradigm, you'd have to kind of figure out everywhere that's touching temperature. It would be a lot of work to kind of go through and make sure like, oh, is this touching temperature? Where is fizz state, percent T being used, etc. Right, it's a lot of grepping. But in this case, it actually just tells you everywhere the temperature is being used. It tells you how it's going to be used. So if you know it's something that's updating T that you care about, then you know to focus on, say, in this case, home or shock or P3. They're actually changing it, changing temperature, and then you can actually focus your debugging efforts as well. So this is just one of the many features that we've implemented to make it easier to work with EAMxx. So now briefly, I'm going to go through aspects of how we interface with the users themselves. So runtime options. So those of you who are familiar with EAM, right, you probably have experienced the name list. Actually, I think all of the components use this. And the name list has some shortcomings, and I've illustrated those on the right-hand side. It's really difficult to read. It's not exactly organized. So if you look on the left-hand side, this is a name list. It's not exactly clear what's necessarily going on. It's incredibly cumbersome to add new options. For anybody who's ever added a new name list option, there are like 4 or 5 files that you have to change in order to make sure that a name list a nameless variable is being distributed appropriately, being read appropriately. So it could be cumbersome, especially to new users, on how to add a new option. And it's difficult to audit, so it's very vulnerable to user error. And I've purposely put a user error in my name list example here, which I'm about to illustrate to you, which I'm going to guess like maybe most of us did not catch just by kind of glancing over on the left-hand side. But in this case, I've listed the same name list option twice. And in EAM, this won't throw an error. Nothing will go wrong. What will happen is it will take the last value it read, which in this case will be 3. So if you, the user, were to open this name list, you would see, yep, cloud mac mech num steps equals 6 right at the top. That's what I wanted. And if you don't scroll down and notice that it's been listed again, you won't realize that it's actually being read at 3. And that could be really confusing. Things are going unstable, but the time step is correct. And it turns out it's actually not correct because you're not subcycling as many times as you would perhaps thought. So to address this, we have switched to a YAML format. And the YAML format comes with a lot of benefits, one of which is that it is at least more human readable. So yes, that's a lot of information on the right-hand side there. This is a typical YAML input. But I think we could all agree that looking at the right-hand side, it's very clear that there are sections and which options are being applied to which section. So there's like a grand physics section within which we see that there is a cloud fraction section and a P3 section. And we see the parameters or the options being exercised on those sections, right? And so it's human readable, so it's less likely and less prone to error. But even more so, we've been able to bake in checks on our YAML parser in order to ensure, and a lot of the sort of common human error, like specifying the same thing twice, or asking for a variable in the wrong format. And so, if it has to be a double format or a string or an array, etc., it checks on that at compile time. It's also easier to add new options. And the reason why is that each one of those sections is passed to its respective process. So P3 gets its whole parameter list. So if you want to add a new name list variable just to P3, you just have to change it in the P3 interface, and then you just have to add it as an option in the name list options. That's 2 files instead of 4 or 5, and you don't have to worry about whether or not you're MPI broadcasting that information everywhere. And lastly, and this is sort of more from comfort for people who are familiar with E3SM, we have atmosphere change and atmosphere query, which are akin to the XML change and XML query that we're all comfortable with. And so this allows us to interface with the runtime options in a way that we're comfortable with, and allows us to then bake in all of these wonderful things like checking whether or not when you change a variable it even exists and you will use and is of the right type. And so if I were to give an example of the name list I just talked about, this is how I would go about changing the number of subcycles. It's very clear. I can query it. It's going to tell me the number. There's only one number. I can only change one number. And it's right there in front of me. This also extends to input and output. So again, looking back at the name list, this is how we control output in EAM. Output streams, like if you want to have different output streams. And looking at this name list, I don't think it's clear to everyone which one of these, or like if you're familiar with this, it is. But just at first glance, you're like, which one of these variables I'm looking at is the output variable? And it turns out it's a lot. So all of the things I've highlighted are all related to output, and they're all related to the same outputs. And so you just kind of like, the output, the variables I want, the frequency I want, the number of snaps maximum number of snaps I'm allowed in that file, and what kind of averaging I want to use. And they're all in different places. And so if you can imagine, if you actually jumped out to like 9 outputs, this would be difficult to parse just human brains. Because if you want to change mfill, you have to know that you want to go to the second indice if it's going to attach to Finkel1. If Finkel1 has 70 variables in it, then your name list gets long. So essentially, it's just can be really difficult to go through. And so a YAML gave us, again, this flexibility and the freedom to make something that's really more readable and much more simple to change. And so I'm going to go through just kind of the different aspects of this and show how EAMxx handles it. And so in the old paradigm, you had to do these Finkels, and it just kind of changed H0, H1, H2. It then appended that to the name of the file, but you didn't really have much more control than that. In EAMxx, you specify a set of YAML files that have all of the information about the output that you want, and you just have to give the path to EAMxx. And then it will open those YAML files, which is what I'm showing now. And in those YAML files, again, we just section off all the individual pieces. This is, of course, human readable. So the field names, for example. If you want to know the maximum snapshots per file, it's clearly identified. The frequency and the frequency units. So NHT frequency does a lot of work. If it's positive, we mean steps. If it's negative, we mean hours. If it's 0, it means monthly. Then the number actually means the actual frequency. And so that's another place where you can make a mistake and not realize it until you start looking at your output and it's in the wrong units. But here it's clearly expressed. And similarly, the averaging type is also clearly expressed. I would also note that we do not have a default output. This is a big concern with any 1024, so 3-kilometer simulations. Memory is actually at a premium, and just dumping a bunch of data we don't want because it's the default output was just not an option. And so in EAMxx, we don't have a default output. You have full control over the output, and you don't have to somehow hack it so that you don't get the default output that you don't maybe want. And I'm going to finish up just talking about testing very briefly. So this is something we're very excited about. We have very robust testing integrated into EAMxx. EAMxx inherits, of course, all the EAM testing, but it also has its own set of robust unit tests. And this is made possible because all of the individual pieces are independent. So what I'm showing here are 2 different examples of where we put this into practice. So on the bottom right-hand side, you can see there's 477 tests being passed in this case, right? And this is one of our nightly tests. And if you look at the time spent, they're on the order of milliseconds, a lot of these. And this is really just testing in granular features of EAMxx. And what this tells us is that if we make a change, we're pretty confident we didn't break something else like completely somewhere else in the code that we wouldn't have expected. And we can test for all these little features. And if one of these fails, because it's such a simple test and it really focuses on just one element, if it fails, it's very quick to figure out what might be going wrong, right? We can zone in on that one piece and really look at it. Similarly, we've integrated this unit testing into our continuous integration on the Scream Git repo. And so that's shown up in the upper right-hand corner. So before a PR can even be merged, it's first tested both on CPU and GPU. Oftentimes this has happened that a developer has done something on CPU and everything works great, but they really actually broke GPU. And that gets detected at this stage before it ever gets into master and starts messing with other people's runs, which might also be on GPU. And so we have this nice gatekeeper in the Git repo integration through the auto tester. And then lastly, I'll just mention that this has been really helpful for debugging because, again, these unit tests are quick and small. They can be run on a single node. They can be run on your laptop. And so when you're making changes and you're doing rapid development or rapid debugging, you can build this suite, run the tests, and then just run the one test that's always failing. And as you're doing debugging and making changes, you can get immediate results. And this is like on the order of seconds. Rebuilding super quick, rerunning super quick. And so it has really helped us to be nimble in our development. And I think is a big reason why Scream has been so successful at getting to where we are now, having this whole new redesign in such short order. So I'll just conclude. I just won't go through these conclusions because I think I'm close to running out of time. But this essentially summarizes everything that I was talking about. So EAMxx is just a complete rewrite. It's a lot of new stuff, but it is, we think, very powerful. And our experience with it has been that it has been very nimble and also is always improving. So with that, I think I will close and welcome questions.
All right, thank you, Aaron.